In this video, we're going to work example problems involving molar mass and percent composition by mass. Percent composition by mass of certain elements in compounds. Okay, so for the first problem, part A says, what is the mass in grams of 1.223 moles of iron 3 sulfate? So the ionic compound iron 3 sulfate, you've got the iron 3 plus cation and the sulfate anion. So these come together to create iron 3 sulfate. Okay, they're saying that we have 1.223 moles of iron 3 sulfate. Okay, but remember, moles is just a scaling factor for a count that you can apply to this count to anything you want, anything that you're saying is an elementary entity for some problem. An egg, a proton, a molecule, whatever, a cation, an anion. It's just like the word dozen. You could say, okay, I've got a dozen iron 3 cations, or a dozen sulfate anions, or a dozen of these iron 3 sulfate units here, a unit of iron 3 sulfates. Okay, they're telling us that if there's 1.223 moles of these, you have 2 iron atoms bonded to 3 of these sulfate units. We have 1.223 moles of those. What's the mass of that 1.223 moles in grams? Well, we know that if we determine the mass in AMU of anything that we're defining to be an elementary entity, again, it could be iron 3 plus cation, a sulfate anion, one of these units, an egg, a proton, a car, whatever. If we determine the mass of that entity in AMU, then that quantity in AMU is also equal to the molar mass of that entity in grams per mole. And so with the molar mass, that's how we have that, we can get that bridge between moles and grams, the atomic world and the human size world. So, okay, what's the mass of one of these iron 3 sulfate units in AMU? Well, we just want to add up the atomic weights of the 2 iron atoms and the 3 sulfate groups. Okay, and so, but we call this a formula weight. This is the formula weight of iron 3 sulfate. It's not a molecular weight. It's not an atomic weight. It's a formula weight. It's based on this is a lattice structure here. Okay, so the atomic weight of iron is 55.845. Okay. Atomic weight of sulfur is 32.06. And then atomic weight of oxygen, 15.999. Okay, add all this up. $399.858. Okay, so this is the formula weight of iron 3 sulfate, but we know that this quantity is also equal to the molar mass of iron 3 sulfate. There's 399.858 grams of iron 3 sulfate for every mole of iron 3 sulfate. And so if we've got 1.223 moles of iron 3 sulfate, and we want to convert this to grams, then we say, okay, for every 1 mole of iron 3 sulfate, there's 399.858 grams of iron 3 sulfate. $489 grams. So the mass of 1.223 moles of iron 3 sulfate is 489 grams. Okay, how many moles of ammonium ions are in 6.955 grams of ammonium carbonate? Okay, so ammonium. The ammonium ion is NH4 plus, and the carbonate anion is CO3 2 minus. So ammonium carbonate is, okay, so we know how many grams of this ammonium carbonate we have. So we can start by converting this to moles to see how many, what's the count of these units here. So let's start by getting the formula weight of this NH42CO3. So, okay, nitrogen atomic weight, 14.007. Then hydrogen, there's 8 hydrogens. Hydrogen atomic weight, 1.008. Okay, carbon, 12.011. And then oxygen, 15.999. Okay. $96.086. Okay, now this is the formula weight of NH42CO3, but we know that this also corresponds to the molar mass. 96.086 grams of NH42CO3 for every 1 mole of NH42CO3. Okay, so we're starting with 6.955 grams of NH42CO3. Now we know that for every 96.086 grams of NH42CO3, there's 1 mole. Okay, so now we're in moles of NH42CO3. So we have a count of these units here, these groups of NH42CO3s. So what is the question asking us? It's saying how many moles of ammonium ions are in this 6.955 grams of ammonium carbonate. So, okay, here's the 6.955 grams of ammonium carbonate as a count. So, okay, in terms of a count for each one of these, how many ammonium ions are there? Well, there's 2, right? You have, for every 1 mole of NH42CO3, you have 2 moles of NH4 plus cations, right? For every 1 of these in the substance, there's 2 of these. So there we go. Now we're in moles of the ammonium cations. 6.955 times 2 divided by 0.145. Okay, what is the mass in grams of 1.5 times 10 to the 21 molecules of aspirin? So molecules of aspirin, molecules of C9H8O4. Well, okay, if we're wanting to relate a count, right? Here's a count of molecules, but a count of anything. It could be anything we want. It could be vehicles, anything we want. If we're wanting to relate a count of something to grams, well, then we need to be in moles, right? So we want to convert this to moles. So how do we convert this to moles, this count? Well, it's the same way we would convert this to dozen. We would divide by 12 to convert this to dozen. Well, to convert this to moles, we divide by Avogadro's number. So we're starting off with 1.5. We want to divide this by 6.022. So 0.002491. So we're starting off with 0.002491 moles of aspirin. How do we convert this to grams? We just need the molar mass. What's the molar mass? It's the molecular weight. The same quantity as the molecular weight. So we've got 9 carbon atoms. 12.011 is the atomic weight. We've got 8 hydrogen atoms. 1.008. And we've got 4 oxygen atoms. 15.999. $180.159. Grams of C9H8O4 for every 1 mole. So, okay, for every 1 mole of aspirin, you've got 180.159 grams of aspirin. So this times 0.449. Okay, calculate the following quantities. Part A, the mass in grams of 0.105 moles of sucrose. Okay, so we start off with 0.105 moles of sucrose. So now if we want to convert this to grams, we just need the molar mass of sucrose. That's going to be the molecular weight. So, okay, we've got 12 carbon atoms. 12.011 is the atomic weight. Got 22 hydrogen atoms. 1.008. And 11 oxygen atoms. 15.999. Okay. $342.297. That's the molecular weight of sucrose, but it's also the molar mass. This is also saying that for every 1 mole of sucrose, there's 342.297 grams of sucrose. $35.9 grams of sucrose. 0.105 moles of sucrose corresponds to 35.9 grams of sucrose. Okay, how many moles of zinc 2 nitrate are in 143.5 grams of zinc 2 nitrate? So we're starting off with 143.5 grams of zinc 2 nitrate. So now to convert this to moles, we just need the molar mass of zinc 2 nitrate, which we can get from the formula weight. So zinc atomic weight, 65.38. Okay. Nitrogen atomic weight, 14.007. Oxygen atomic weight, 15.999. Okay. $189.388. So for every 189.388 grams of zinc 2 nitrate, there's 1 mole of zinc 2 nitrate units. So 143.5 divided by, so 0.758 moles of zinc 2 nitrate units. Okay, how many molecules are in 1 times 10 to the minus 6 moles of CH3CH2OH? Well, this is easy. Okay, so we're starting off with 1 times 10 to the minus 6 moles of CH3CH2OH. Okay, well, to convert this to molecules, it would be like if they asked how many molecules are in a certain number of dozens of these molecules. Well, you're just multiplying by 12, right? How many eggs are in 3 dozen eggs? There's 36. Well, how many molecules are in this many moles of this molecule? Just multiply by the Avogadro's number, right? Because it's for every 1 mole of these molecules, there's 6.022 times 10 to the 23rd of these molecules. It'd be the same idea if we put dozen here, then this would be 12. So 1E. So 6.022 times 10 to the 17. molecules. CH3, CH2OH molecules. Okay. How many nitrogen atoms are in 0.410 moles of NH3? Okay, so we have a count of NH3 molecules. 0.410 moles of NH3. That's a count, right? We could easily convert this to like an actual, okay, the count of NH3 molecules. And since we're trying to count nitrogen atoms, let's do that. So for every 1 mole of NH3 molecules, you've got 6.022 times 10 to the 23rd NH3 molecules. So now we're in individual NH3 molecules. So, okay, in a certain count of NH3 molecules, how many nitrogen atoms are there? Well, it's the same count, right? It's the same. If you have 12 NH3s, then you have 12 nitrogens, right? So it's the same number. I mean, we could just write this out for clarity, but we're really done. So for every 6.022 times 10 to the 23rd NH3 molecules, there's 6.022 times 10 to the 23rd N atoms, right? You see how we didn't really technically need to write that, but if we want to be clearly in terms of nitrogen atoms, there you go. And these cancel. So now we're in terms of the count of nitrogen atoms, 0.41. Well, okay, no, let's do these cancel. Okay. So 0.410 times 6.022, 2.47 times 10 to the 23. Okay, all of the substances listed here are fertilizers that contribute nitrogen to the soil. Which of these is the richest source of nitrogen on a mass percentage basis? Okay, so for each of these, we want to determine the percent composition by mass of the nitrogen in the compound, and then state which one's the largest. So how do we do this? Well, all we're going to do is, let's start with the urea. We want to determine the molecular weight, or is this a formula weight? Yeah, I mean, depending if this is a molecule or a lattice type structure, it's going to be the molecular weight of the formula weight of the compound. So that's the total weight of the compound. And then we're going to get the percentage of that weight that's associated with nitrogen. So in this case, we're going to have 2 nitrogen atoms. So, okay, we've got 2 nitrogen atoms. Nitrogen atomic weight, 14.007. We've got 4 hydrogen atoms, 1.008. We've got a carbon atom and an oxygen atom, 12.011, 15.999. So 60.056 AMU. Is the molecular weight of this compound. Now, what percentage of that weight is nitrogen? So all we do is we say, okay, 60.056 AMU, and then we've got 2 nitrogen atoms. So that's 28.014. And we're going to get this as a percentage. %46.6%. That's it. That's the percent composition by mass of nitrogen. in urea. So now we want to go through this same process for these other compounds. Okay, so ammonium nitrate, we've got a single nitrogen, so 14.007, plus, once again, 4 hydrogens, that was 1.008. Oh, no, we've got 2 nitrogens. Okay, NH4NO3. And then 3 oxygens. That's 15.999. So let's see. 2 times 14.07, 4, 1.088, and then three times, okay, 80.043. So now we've got 80.043 AMU is the entire molecular weight, and then 2 times 28.014. Okay, so this divided by, so 35%. Okay. Okay, now guanidine, we've got, so 3 nitrogens for 5 hydrogens and a carbon. Carbon was 12.011. So 3 times 14.007, 5 times 1.088, and then 83.094. So now we want to divide the nitrogen weight by this, 50.6%. Okay, now last is ammonia. So we've got a nitrogen and 3 hydrogens. Yeah, this is going to be a large percentage for sure. So 3 times 1.088 plus, now take 14.007 and divide by this, 82.2%. So the answer is ammonia is the richest source of nitrogen on a mass percentage basis. Not an atomic percentage. On an atomic percentage, this is 1 in 4. This still might be the largest atomic percentage, but now probably this 3 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 to 9. So no, this still probably would be the largest atomic percentage, but from a weight percentage basis, this is the largest, ammonia.